thank you. Those who were at the workshop yesterday will recognise some of the bits that can't hear, I'm afraid. That's life. So I'm going to talk about these things. This is a violin, those who don't live in this building. But I'm in an engineering department, and so really what I'm going to be doing in this talk is taking this. I mean, you think it's a sort of pretty artistic object, but it's an engineered object, it's a man-made thing. And I'm going to treat it in the kind of way that we often do when lecturing to engineering students, of teaching them to design. And design may or may not be done in a systematic way, and it pays to think about what you're trying to design before you start, and so on. So we always try to tell them. So you know what reverse engineering is? Reverse engineering is when Samsung buys the latest Nokia and takes it to pieces to find out how they've done their particular new widget. So we're going to take this thing that we've got and we're going to sort of reinvent it and decide how much of it we end up with again and how much of it is decorative up to a point. And I will do some unashamed cherry picking in the course of this talk. It's mainly not a cutting-edge research talk, it's a sort of ramble through the background of why the violin is the way it is, and it touches on various things where there is current research going on, but that's not the main focus. Is just to look at this object in a systematic way. If we didn't have it and you were asked to make a thing a bit like this, what would you find yourself making? So, here are some violins, and here's what they ordinarily sound like. Let's have just a little snatch of music. Music you get, all the rest will be noises. One little bit of music to remind us who we are. So this is a talk which ranges over a number of academic disciplines. So we start with the one slide of history. So what do we know about bowed-stringed instruments like this? Well, the idea of making noises mediated by resin that comes out of trees seems to go back as far as there is any written record or historical artifacts. People seem to have discovered you've got this stuff from trees on your fingers, you could squeak things and make noises on them. So the basic idea seems to be there for a long time. I'm going to be concentrating on the kind of Western classical world here. There are lots of other cultures that use bowed-stringed instruments, but just for definiteness we'll focus on the violin as understood in places like this that do Western type music. And in terms of potted history, the kind of people who invented the violin had already been making things a bit like this for about 100 years before that. Before the violins, we had the viol family, something like 1450, the earliest ones of those. They're the same sort of thing. They're strings, they're wooden boxes, you play them with a bow. People were prepared to pay money for them, so there were makers. Famous names like the Amati family were viol makers before anything violinish came along. So something like 100 years after that, you find the first recognisable violins. And the first recognisable violins look absolutely astonishingly like violins. So somebody, rather quickly after they first started, had a really good idea and got all kinds of details, and really only rather small changes have been made since then in the sort of classical violin as exemplified by this one that I'm holding here. Curiously enough, I believe the earliest authenticated surviving violins, there were all sorts of things in museums which were claimed to be old, and nearly all of those have been questioned by art historians as being later fakes. And I believe it's still the case that the unquestionably oldest verified violin is there's an altarpiece in a church in Germany somewhere, I can't remember exactly where, which has, angels with musical instruments, and it was old and dusty, and people assumed they were all carved out of wood until they eventually got up and did some restoration work on it, and they found that the sculptor had actually put real instruments into this wood carving, and so they had actual violins, I think, and other instruments as well, and there was no doubt about the date of this church altarpiece. So Nothing whatever to do with this talk. About 100 years further on than that, you'd come to the violin maker that everyone's heard of, Stradivari. So by the time Stradivari was building, Italians had been making things rather like this for about 100 years, from families that had been making viols for 100 years before that. And ever since then, people have been copying what he did, more or less, with variations. So, let's move on from history to woodwork. Next class session. Now, if you all know what violins look like from the outside, but maybe some of you haven't looked at the inside of one. Here's a sort of exploded view. And there's just a few things that you might not have been aware of. The thing you're least likely to be aware of if you've never looked into the holes in a violin is that on the inside, it's not as symmetrical as it looks from the outside. It looks left-right symmetric from the outside. It isn't symmetric on the inside, and we'll come to the reason for that towards the end of the lecture. So here's our violin conveniently cut in half. We won't do that particular demonstration in the lecture. But underneath the bridge, underneath 1 foot, there's a kind of strut called the bass bar. Here you see it here. It doesn't run all the way from end to it. It's about 3/4 of the length and sort of tapers away. Makers worry a lot about the exact shape of it. So there's a kind of reinforcement bar there. And then even more surprising, roughly underneath the other foot of the bridge is a little piece of stick, the soundpost, which is just kind of wedged in. What's that for? Well, we'll talk about that later on as well. All the rest, well, we'll see some woodwork in a moment. It's made of various different pieces. The violin is put together very much in the way that you see from these pictures here. These various bits are made separately and then assembled. So here's a traditional violin maker. This is Juliet Barker, that I learned my limited knowledge of violin making from, based in Cambridge. So here she is working on various bits of, probably a viola in her case, because that was her special niche. And you can see various bits arrayed around her here. If you thought that these curved back and front plates were made by somehow getting a big steam press and taking a flat piece of wood and pressing it, then you'd be wrong, or at least for almost all makers, almost all the time you'd be wrong. Nearly always these things are carved out of the solid. The only part of a violin which is made curved by being bent are these thin pieces along the side. Everything else is carved out of solid lumps, and you can see some of the processes here. Basically, you do the outside first. You start with the great big gouge, like this one here, big shavings. Then you go on to these wonderful little violin makers' thumb planes here. Then you end up with scrapers, and she's using a scraper in the picture here. You do the outside first, and then you turn it over and you hollow it out. Here she is working on hollowing out a back, and she's keeping an eye on the thickness distribution with her thickness calipers conveniently to hand, so she can check how the distribution of thickness, and all kinds of other violin makery paraphernalia sitting around. There's a bunch of gouges that are carving scrolls. There's a string of bridges hanging in the window. All the sorts of things that you see in violin making workshops. Here she is doing another stage. Just illustrates something of the constructional sequence. This piece of stuff here doesn't stay inside the violin later on. This is just a mould which is used to define the shape. So it's got these corner blocks. You glue those onto the mould, you bend these side bits and you glue it all together. You make the back and the front one way or another so the outline matches, and then you assemble it all at some crucial stage in the process, removing this piece from the middle. Different makers have different detail sequences. Her sequence, she was Mittenwald trained, and so this is the German method. At this stage, these ribs are already glued onto the back with the mould still in place. She's all ready with the top to close the box. So what she's about to do is go around with a little hammer, tap these blocks and unglue them from the mould and slide the mould out from inside, and then put the top on and glue it on. And then after that, you know, see, here's the bass bar. You can see that rather clearly here. You never see the inside again until something goes wrong after that. Different violin maker's shop, just to show some of the kit of parts. So here are two big slabs. That's going to be a back and that's going to be a top, seen in the solid. An inside mould, a subtly different pattern of mould, because a maker with a different tradition of training. Experts may notice that he's one who cut his neck mortise before he put the back on, because it was easy to do the saw cut, so he did his mortise at that stage. But otherwise the same sequence. Here's a back joint onto some ribs, a couple of scrolls. Here's a back with its outside arching roughed out, but its details not finished, and there's a lot of wood shavings, because there's always lots of those around. So, turning to the engineers then, what's the point of a violin? Well, presumably the point of a violin is to make sound. Now I'm going to take an unashamedly crude view of things here and see how far that takes us. That's not just because I have an innate wish to be crude, it's the right way to approach things. Always do the simple things first. It's the hardest message to teach graduate students, is don't start doing complicated things till you're sure you've understood the simple things. So ask yourself a simple question, see how far it takes you, and once you say, okay, no, it really is more than that, then ask the next question. So, I don't know if this is still academically respectable, but a school of thought about how did the violin arise from the viol family was basically in order to be louder. The viols were not, on the whole, made for playing in public concerts in big halls. They were played by aristocratic people in their drawing rooms, or they were played by paid musicians for aristocratic people while they were eating their dinner. They didn't want other people to hear it, they were paying the salaries, they wanted refinement, they didn't want loudness. But you can do other kinds of music than that on bowstringed instruments, and so I don't know whether they were thinking of bigger audiences or thinking of outdoor music and dancing, but the idea of taking something a bit like the viols, but something you could have the hoedown on, louder music. And so let's just ask, suppose that's the only thing. Suppose all we want to do is that we want to reinvent something like this. It's going to have strings about that length so we can conveniently hold it up while we're calling the dancing or something. So it can't be too big. And all we ask is that it's as loud as possible. Strings of convenient length to handle, not too heavy for me to carry around while I'm walking, make it as loud as possible. And probably that's not the whole story, we'll come back to that, but let's see how far that takes us. How do we make sounds loud? Well, this is a good question to ask because we know how to answer that question. Always ask yourself questions you can begin to answer. The issue there, what determines how loud things are? Well, how does the violin work roughly? Roughly what happens is the player spends their entire time trying to manipulate the string to do certain things. That's all they actually care about. Making the string play the right frequency, the right kind of transients, with particular magic bowing gestures they spend hours and hours practicing. That's all, they don't care about the woodwork, that's just they hold the string up. And the problem is simple, here's a stretched string, and I'm plucking it, making a noise on it, and you either can't hear it at all or you can hardly hear it. A string is a lousy way to make sound waves. If you want to make pressure waves in the air, you need a vibrating structure, but it's got to be a structure which is roughly as big as the wavelength of sound at the frequencies you're interested in. When this little, here's a 1 millimeter string, it's vibrating at a few hundred hertz, wavelengths of sound this big, much, much bigger than the string, and the string vibrates through the air and the air just flows around it. The air has no reason at all to get compressed in front of the string and rarefied behind it, it just moves out of the way. So we need to get our strings, so strings are good from the player's point of view at doing these tricks you want them to do. That's another story about exactly why strings are a good thing, but they're no good at making noise, so we need an amplifier of some kind, and all this woodwork here is a kind of mechanical amplifier. So what determines how loud it is? Well, what is happening is that the string is vibrating from side to side. The string, of course, is under tension, so there's a tension force pulling always along the string. As the string moves a bit to the left and a bit to the right, that tension force pulls a bit to the left and a bit to the right at the bridge. So there's always this steady component of tension, but there's also an oscillating component of tension which applies a force at the top of the bridge in this direction. And so you've got this big tall bridge here, you apply a force here, the bridge can kind of rock around in its plane until the 2 feet of the bridge put forces up and down on the top, and that might make these bits of wood vibrate. They're bigger compared with the wavelength. You get all this structure vibrating, and maybe you can make some more sound. So that's what's going on. So the thing that governs how loud it is simply how quickly does the energy get out of the string through this notch in the bridge into the rest of the structure. So what governs how energy flows from one vibrating structure to another. Well, we know the answer to that. It's governed by something called impedance. Any object which vibrates, every object vibrates, anything at all which vibrates has a quantity called impedance. And all that means is that we have this lid here. I decide I'm going to make it vibrate at this point here. I say I get hold of it here. I am going to force it to vibrate at some frequency that I choose with a certain amplitude, 1 millimeter, shall we say. How hard do I have to press? That's the impedance. How much force do I need to produce vibration of a given amplitude at the frequency that I choose? Then there's a result, sort of physics kind of result, which says if you take two things and you couple them together, so here's a kind of schematic string and a bridge and a violin body here, suitable for drawing in the PowerPoint graphical tools. And the string has an impedance, the body felt through the bridge has an impedance. The thing that governs how much the energy leaks across this join from the string into the body is simply, are those impedances very different or are they very similar? If the impedances are very different, the energy can't get through the join easily. Most of it stays in the string, gets reflected back. If the opposite extreme, you make the impedances equal, and then the join becomes invisible to the vibrations. The energy goes straight round and all of it will go straight out of the string. So if we want to make things loud, we want to push the impedances towards matching. Now it is obvious, is it going to say that? Yes. It is obvious that the impedance of a string is lower than the impedance of a violin body. I don't have to press so hard to make the string vibrate. I need to press harder to make the violin body vibrate. So the string is lower than the body. I want to make them more equal, so I've got to bring the string up and the body down. So how do you make louder instruments? You put heavier and heavier strings on them, and you make the body lighter and lighter and lighter. And sure, that works. That makes louder instruments. But, of course, something else goes wrong. Look at a bit of data here. For a typical set of violin strings, modern standard violin strings, so here are the 4 open strings, there are the frequencies they're tuned to, and here are the tensions in round numbers, and I've just expressed them in kilograms weight so you can visualize them. So those are the typical tensions of a set of violin strings, fairly high. You add those up and you get about 20 odd kilograms. They then pass over the bridge with quite an angle here, 25 degrees or so, and all the simple trigonometry calculation reveals that the down bearing force through the bridge is something like 10 kilograms. And this is something like 10 kilograms, provided specially for this purpose. That is what is sitting on the front of your violin all the time. That's sitting on a piece of softwood that's about 3 millimeters thick, may well be less. Sometimes I pass this round the audience just to really love the students of these sort of, flimsy musicians, you know. What is bearing down on their violin. So people have gone a long way with this process. Much less far, much further than with the viol family. And of course, what limits this process is not that you reach a point when people say, whoa, that's too loud. You very, very rarely hear a violin player complaining that an instrument is too loud. What happens if you keep putting heavier and heavier strings on thinner and thinner bodies is they fall apart. So we need to go back to our list of design objectives and forget about sound for the moment. And we better start thinking about strength. If that's where we want to go, to have the lightest possible body and the heaviest possible strings, we better put a bit of ingenuity into making sure it doesn't fall apart too often. And the number of these features, which at first glance, I mean, we've already seen this is an object from the Renaissance, and it kind of looks it with all these twiddly shapes. Surely all this twiddly stuff is purely decorative. Well, let's have a look at some of these twiddly things. Lots of the features of the violin design contribute to strength. Contribute. I'm not saying that's their only function, but that's part of the deal. I've already mentioned, for example, that arched plates rather than flat plates. You don't build a violin like a guitar box with rather flat plates. Everything is curved. You struggle to find a flat surface anywhere in this. Well, if you're trying to make a thin plate and then put a load on the middle of it, that's the kind of thing that are called bridges in the ordinary jargon. It's rather common, isn't it? You make a bridge arch-shaped rather than flat, and it bears the load with a lighter structure. That's standard engineering design. So that all makes sense. So curves everywhere. You get better strength from the same amount of material. Well, there's a soundpost and bass bar that I mentioned earlier. Well, this isn't the only thing those are doing, but I'm sure it's no coincidence there is some kind of reinforcing structure underneath, more or less, the two places where this load is being applied through the feet of the bridge. We've got a strut under one, and we've got a pillar under the other one. That seems quite good. I strongly suspect that's how the soundpost got invented, is that somebody took something a bit too thin, started tuning the instrument up and heard ominous noises and said, whoa, wedged in a bit of reinforcing, and then, oh, I quite like this, you know. And how else did anyone ever think of doing that? So I suspect it was a kind of emergency measure, and it turned out to sound good, but we'll come back to that right at the end. Strength. Now the holes, for reasons which I'll explain in a little bit, there are good reasons for having holes in our box. So we've got this thin box, which is highly stressed, and we want to make holes in it. Now that's bad. Holes are a natural focus for cracks to start. Every owner of a violin knows that cracks do start. And the thing now, there's probably a good reason for these holes being slot-shaped, to make this beat around the bridge particularly flexible so you can get it vibrating rather well. If we just cut rectangular slots in our plate with sharp corners at the end, it will take no time at all for you to have cracks growing off down the front from those corners. That's what engineers call stress concentrations. It's the reason aeroplanes have round windows and not square ones. It's because when they built the first commercial jet liner, the Comet, they had a number of crashes because some architect type thought square windows would be nice. And they weren't a good idea because there's two cracks growing, and no one builds square windows in airplanes anymore. So we want a slot, and we don't want it to have a tight curvature at the bottom for the stress concentrations. So what do? Well, how many choices have you got? You've got your slot, you need to curve the end off. You either curve them both the same way and you get C shapes, or you curve one the other and get F shapes. Well, the viols have C's and the violins have F's. As such, it doesn't make much difference, but there's a reason for sinuous shapes. And the two things that make immediate sense can both be found in instruments of this general kind. Purfling. You ever heard of purfling? If you've never looked closely at a violin, you might have noticed there's a kind of black line around the edge. And again, if you just glimpsed that and didn't look very hard, you'd probably imagine it's painted on. Well, if you pay little enough for your violin, it is painted on. But in upper-class violins like this one, it's strips of wood, or strips of something, inlaid in about halfway through the thickness of the top. Rather a laborious exercise. It's deeply significant to the culture of violin makers. It's the first thing they look at when they're handling each other's instruments, is to see how they've done those corners in purfling. As such, I don't think that has deep significance. It's just a cultural thing. But the fact of having this purfling here is probably, as well as being kind of pretty, helps with preserving things, especially for the top, for reasons that we'll come to in a moment. We use a softwood, a nice straight-grained wood that would split very easily for the top. And especially these bits at the top and the bottom where the end grain runs off the plate, they're very vulnerable. You get a knock there and it's really very easy to get a crack started. And players are always giving these knocks. They shouldn't be trusted with instruments. So if it was an exposed end grain here, liable to start cracks, the idea of gluing into it a strip of stuff running across the grain is quite sound, really. It's going to help to discourage cracks from growing, and maybe a bit nice. And finally, or at least finally for this list, what about material? What are we going to make our new thing out of? They used wood. Well, what choice did they have? They didn't have a very wide range of materials available. Now here is something where you would be justified in thinking, surely that's something we would do different now. Well, we've got a much, much wider range of materials available to make things out of now. There's no doubt about that. Would we still choose? What should we choose? How should we decide? Well, there's an answer to that question, and it's a little bit surprising. This is the most technical part of this lecture. But let me explain this diagram. Let me point at this violin bow. This is a diagram stolen from a splendid textbook called Material Selection for Engineering Design, which I recommend to anyone who's interested in this sort of thing, which I'll have to explain to you. Now, this is a summary of relevant properties of every known material. Now, materials have lots of properties. These are two particular properties that matter for vibration. We've got along here, you probably can't read the small print, but we've got along here, we've got density. How heavy is a given volume. And up here we've got Young's modulus, which is a measure of stiffness, how hard you have to press, how pull to stretch it. So we've got stiffness against density. And for any particular material, polyurethane or brass or carbon fibre composite, whatever it may be, any particular material has a particular value of density and a particular value of stiffness. More than one, but that's a subtlety. So it's a dot on this diagram. Each individual material falls somewhere on this diagram. The scales are logarithmic, so we're covering very big ranges here. Anyone really wants to know, you have to come a little later and read the small print. So there's a dot on here for every material known to man, and then there are blobs drawn around related families of things. So here we've got all the polymers, for example, so all the engineering plastics. So we've got PTFE, that's the non-stick saucepan stuff, high density polyethylene, what you make your washing up bowls out of, nylon, PVC, polycarbonate right at the top, that's another high performance polymer that you make plastic, bulletproof windows, that kind of thing out of. So all the polymers. This kind of curvy triangle thing here is all the metals and alloys. Right at the top there, touching the very top of the diagram, is all the engineering ceramics, which includes mostly rather exotic things. Right at the very top we have diamond. It's got a kind of moderate density, but it is the stiffest material of all things known. So it's got the highest Young's modulus. Over here we've got, what have we got? We've got elastomers, we've got rubbers and things like that. Over here we've got foams. Foams disappear off this bottom corner of the diagram because depending on how much air you blow into your foam, you could make it very, very low density and very, very low stiffness, and they extend off over there. Finally, here we have woods, and woods appear twice on the diagram. You choose a sample of a particular type of wood, and of course there's only one value of the density. But you've got two values of stiffness, or at least two, because woods are all stiffer along the grain, perpendicular in the tree, and less stiff across the grain, so radial in the tree. So each wood, like ash here, appears twice because we've got parallel to the grain and perpendicular to the grain stiffnesses. So is that clear? So here's this summary. What's the point of that? Well, we can do a little calculation. I'm not going to do it here, but if anyone wants to know, I can tell you how to do this. To say, I'm going to make a violin out of any one of these materials. What will determine how loud it is? And so what we can go through a little rather simple design calculation to say we're going to make something, it's going to be this size, it's going to have resonant frequencies that are in the usual place for a violin body. I will adjust the thickness to achieve that. Right? How loud will it be? And it turns out that there are particular lines in this diagram with a particular slope here on these log scales, where any 2 points along this line would make violins which were equally loud. So if you made a violin out of lead here and silicone rubber here, they would be equally loud. That's not very loud, it would not be an easy thing to do in either case, but they would be as loud as each other. We want to make things louder. We have to take this line and roll it across the diagram and push it as far that way as we can go. And what is the very last material we come to? We push these lines over to here. It's over here in the wood island. It outperforms every other easy material. Not quite true, but nearly. So wood is not such a silly material for this particular business of making mechanical amplifiers that are loud. Wood is quite a good idea. Now here's a zoom of the bit just to do with wood so you can see it a bit more clearly. So here are the various different kinds, again, perpendicular to the grain and parallel to the grain. And we'll concentrate on the parallel to the grain things here. And these are lined up much as you'd expect. All the sort of heavy, chunky woods like oak are over here, and they're not so great for making violins. Right out on this end of the balsa woods, the lightest woods you can find. Balsa covers quite a wide range. Balsas, well, people used to laugh at this point and say balsa wood, yes, balsa wood would be rather difficult to make violins out of because it's so soft, surely no one does that. Actually, in recent years, you try Googling on balsa wood violin, you'll find some interesting material on the web now. People have been doing some quite interesting experiments with balsa wood. I don't think it's going to replace professional violins, but there are people who say it may have a future in making satisfying violins for beginners. That's not an unimportant thing as well. To make a violin for beginners, which is pleasing to play rather than sounding horrible, and maybe a future in balsa wood. But generally we back off from that a little, but as little as we can get away with. And the next thing we come to once we lose the balsas are the things, are the coniferous woods before we get to the hardwoods. So we've got the spruces, firs, redwoods, and then all the heavier things over here. Technically, balsa is a hardwood, but that's a botanical distinction. Most violins are made of these sorts of things, rather carefully selected softwoods, spruces mostly. Why? Why is wood so good? Well, here's an electron microscope picture of a piece of instrument quality spruce. So this is a little piece at the top of this violin here, say, which has been cut with a rather sharp knife, almost exactly parallel to the grains. And what you're seeing here, you see the individual wood cells looking like tubes. And the structure of this wood is like a box of drinking straws, basically. Yeah? Each wood cell is a thin-walled tube. They're squarish drinking straws, but with a lot of empty space inside it, and they're all stacked together. Right? That sounds like running a bit of glue down your box of drinking straws. Lots of space down all these tunnels here. And that's a very efficient way, because wood is made of a polymer, which is not so different from those other polymers that were on the diagram, but because it's been structured with this microstructure with a lot of empty space, this is just a really good way of getting high stiffness to weight ratios in the particular combination that you need for this loudness. So it's not magic, it's the microstructure of wood. Well, there's a whole subject that's developed in recent years called biomimetics, of looking at natural materials which have evolved to have immensely clever microstructure, and people trying very hard to duplicate not only wood but seashells and cuttlefish bone and human bone. Also, a lot of those have extremely high performance properties because evolution has driven them there, and people are trying very hard to make man-made materials that take advantage of some of those things. We can't quite do this yet. We can do it on a bigger scale. Every time you're on an aeroplane, you're standing on something with structure a bit like this. In the middle of aeroplane floor panels is a sort of aluminium honeycomb. If I was at home, I'd have a piece with me, but you have to imagine aluminium honeycomb in a sandwich panel with metal plates, so you don't see it, it's inside. And it gives you a very light, stiff floor, which is what you need for aeroplanes. What we can't do is make things with that kind of structure small enough that you can carve an arched shape only 3 millimeters thick out of it and not see the individual holes. So we know how to make things a bit like this. We can't yet make them at this small scale. It may come, but at the moment, wood is still outperforming. If you do just the best possible tricks with other materials, you can just about get up to the same performance of wood. That's a fair statement of the composite design strategy. You can't beat it, you can just about join it. But wood, we think of wood as an old-fashioned material. Here are some spruce trees near Mittenwald, just the kind of things that the Germans would cut down to make violins, but really, wood is a high-tech material, which just happens to grow on trees. I want to do one more thing. We will eventually come back to sound, but I want to just do one more thing on this list of design objectives. So we've said a bit about sound, we've said a bit about strength. There is one other thing to point out. It may matter less for this audience. This is really important for engineering students, though, because it's a thing that designers these days often don't care about. But with the Great Green Revolution, we should be beginning to care about this much more. This looks like an old violin, but is a brand new one. The most expensive violins in the world are quite old now. And yet, they've got all these kilograms sitting on them and they've been bashed around their players for centuries. How have they survived? Well, they haven't. They've all been broken and repaired many times. So, the fact that they have been able to be repaired and still come back into good order is part of the good design. Designing something so that it is possible to maintain it. If you're expecting something to have a lifetime in centuries rather than just a few years, you should think about that at the design stage. You ever tried to mend a washing machine? You see this screw on the outside, you think, I expect we undo that, and you undo it, something inside goes clunk. You spend ages and ages and ages trying to get that bit to do back up again, because they don't want you to do that. Now there are at least two features of traditional violin construction, design and construction, which are still followed, which contributes to this ease of maintenance. If you get a major difficulty with a violin, a big crack or something, you've got to get inside it to fix that properly. So we've got to maybe open the box up. And having opened it up, we've got to be able to put it back together again so that it looks okay still. And there are two ingenious features of the design which help with that. First of all, we've got to glue the box together. Now if we use glue which is too strong, then you're trying to open the box up and you don't go through the glue, the chunks of the wood fall out, so then you've got a major repair job in your hand. You use glue that's too weak and it falls apart of its own accord. Glue that's just right. It's just a bit less strong than the wood, so that you can open the join carefully, but so that nearly all the damage is confined to the layer of glue. Means you get the top off, you haven't damaged the structure, you just clean it up and you put it back together. So you need to choose the right sort of glue for that, and violin makers still use old-fashioned boil up in a glue pot glue. Gelatine comes from various, usually animal sources, horns and hooves and rabbit skins and fish, things like that. And they make a lot of fuss about subtly different variants of it. It's all basically the same stuff. Chemically, it's the same stuff. Lots of parts of your body are made of. It's the same stuff as keratin. Not keratin, collagen. Just the molecules untwiddled. And it has two very important properties. One is that it's not too strong, or at least you can mix it in a way that it just satisfies the strength requirement. The other thing is that it does something which nearly no other modern glue does. You glue something together with the kind of white or yellow stuff that comes in a bottle, and it sticks fine. You have to get it apart, maybe you can manage to do that. You come to glue it back together again and you've got a problem. All those polymeric glues, once they've hardened, leave a surface which the new glue does not like to stick to, because all those cross-links have formed between the molecules and the new glue won't stick to it. Gelatine softens in hot water, so you can just take the hot water brush from your glue pot and wash around it carefully. You soften the glue and it actually sticks a bit better the second time. It's called sizing in the trade. Washing around with a weak glue solution before you do the proper join is actually part of the technique. So it's a glue which can stick to itself again. Quite important. You'd struggle to buy another one anywhere in your hardware store that can do that. There is one final feature that helps with this. I'm not going to do this. Sometimes I demonstrate this, what I'm doing, when I give this lecture, but not on this sort of violin. I keep one specially for that, but I couldn't bring it in my hand baggage. How do you open a violin up? Don't try this. As they say on children's TV, don't try this unless there is an adult present. What you do is you take a knife, not a sharp knife, but a table knife or an artist's palette knife, and you insinuate it into this glue join between the top and the ribs. And you work it round and you get horrible cracking noises, which with a bit of luck are just the glue line breaking and the top comes off. And I've said all this spiel about how you hardly do any damage, it's the glue that fails, but there's always a little bit of damage. So then you've got to put it back together and give it back to the owner, and it's still got to look nice. Now, you try doing this on a guitar, and it's a real pain to do, because a guitar is the same kind of thing, a wooden box, but the edges are joined where the sides of the top join in a flush join with a little inlaid strip around it. And when that top's been off, you can always tell there's always some residual damage. It never looks as nice again. But the violin has an ingenious little feature, which is that the edges of the top and the back overhang a little bit. Now this is a brand new one, so it's rather clean, but once this has been in the hands of players for a bit, it'll have a layer of black crud collected in this little crack here, and that's the place you run your knife round. And then you little bit of damage, but nobody can see. You put it back together and it soon fills up with black crud and nobody can really tell. So just that overhanging place to put the point of your knife and to conceal the little bit of inevitable damage makes all the difference. Because all those famous violins that cost millions have all been opened many, many times in their lives. In fact, it's remarkable what a high proportion of non-original wood is in all these famous so-called violins, but that's another story. So, finally we got back to sound, and now before too long we'll have some sound demonstrations. So I'm going to say a few things about sound, and let me make it clear right from the beginning that up to now I've been somewhat systematic in what I've said, but from now on I'm unashamedly cherry picking. I'm going to tell you a few things that I happen to know the answer to, which are part of the story. and they're easy, they're bits we can put across, they're important in their own right. Are they the most important? Not necessarily. Are there lots of other important things? Yes, there certainly are, but let's have a few nice things. So there's one question we might ask ourselves. Okay, this box is an amplifier. Well, we know about amplifiers now. They have black fronts and knobs on them. They live in racks like this. And when you go buy one of those from the hi-fi store, you know exactly what you're looking for. The kind of amplifier you have to pay a lot of money for is one which just amplifies. It amplifies all frequencies the same amount, so that it doesn't distort the sound you put in. So everyone knows that a perfect amplifier is something whose frequency response is flat. It doesn't interfere with the sound. Now, is that what they really wanted to do for the violin? Would the perfect violin be one with a flat response? It's not an unreasonable question to ask. Real violins certainly don't have flat response. This blue plot here is a typical example of the frequency response. Here's frequency along here from the lowest note of the violin up to 5 kilohertz, high-ish frequencies. And here's the response in some way. The details don't really matter. All that matters is that it's a wiggly line. There are some frequencies where you get very strong response and some frequencies where you get very weak response. It certainly isn't flat. If that was your hi-fi amplifier, you would not want to pay a lot of money for it. All our speakers did that. You would grumble. So maybe. Now, mechanical amplifiers inevitably do this sort of thing. The reason for that, yes, I'll come back to this slide in a moment. Each one of those peaks corresponds to a particular vibration of the box, because the violin body is, as well as the string, is a vibrating object in its own right. It makes a noise when I hit it. It has its own resonances. So, courtesy of George Stepani, some people here know, that's an animation of one particular vibration resonance of a typical violin. It's not the same one that you saw the plot of just now, but that doesn't really matter. And here's another one. 540 hertz. You can look a bit to see what it's doing. The details don't really matter, except that it's vibrating in some complicated way. Each one of those peaks in that plot corresponds to a resonance. The higher you go in frequency, here are some other resonances visualized in a different way. This is a laser method of visualizing things where these are essentially contours of vibration amplitude. So as we go to higher frequencies, we get more and more smaller and smaller islands of vibration. And in some sense, that pattern of resonances is the acoustical fingerprint of a particular violin. That's what makes one violin different from another, is that the shapes, the frequencies, and the strength of driving of those various resonances are different. So all the things you pay a lot or a little money for are to do with manipulating these. So somehow we care about resonances, but would we rather not have them? Now I'm going to inelegantly slip back to this thing here. Well, would we rather it was flat? Well, I was going to play you the sound of a violin with a flat frequency response. So I'm going to play you a little snippet from a commercial recording, a well-known passage from the Spager's Violin Concerto, and then the same passage played on a violin with a hi-fi frequency response. £1 million for that one? Probably not.
Is it a synthesized or is it?
No, it's real playing. It's the sound of a sensor just measuring the force, sound and then amplified through, I presume, something with a flat frequency response. And it's the real thing. Yeah. So, something not right about that. What's going on? Well, we're going to talk about one aspect of that. Now, this lumpiness of response curves has a number of consequences. The thing about it which obviously looks bad is that, and where a flat response might be good, is that it's going to be inevitable that this violin with this blue curve is not going to sound the same from one note to the next, because the response is sometimes high and sometimes low on the various harmonics, and So you can't have a perfectly even violin with an underlying response like that. Is that good or bad? Well, too much of it, unevenness, is bad. Is a bit of it bad or good? Interesting question of current research. I'm going to concentrate on one particular aspect of something which this jaggedy curve creates for us, which is something to do with the way that violinists play. And perhaps let me get my glamorous assistant to do the first demonstration here. Now, Western violin, not all violinists everywhere in the world do this, but typical modern Western violinists have this horrible tremor. They have a tendency to be quite unable to play a steady note. They're always doing vibrato. Now, vibrato does something to the sound of a violin, which I just want to remind you is rather different than when you wind up the vibrato knob on your Yamaha keyboard. It sounds nicer than the keyboard. And she's just going to play you a note where she'll start without vibrato and then gradually wind it in and then back down again. Just once more, get really fruity. It's a key resource of violinists to do that. Now that somehow doesn't sound the same, does it, as when you wind up the vibrato on a keyboard instrument. There's something less unpleasant about it. Now why is that? The reason for that is to do with, now here's that same jaggedy blue curve again here, and here's a particular note being played. It's the note that you would ordinarily call B flat, but my keyboard can't do a flat, so it's called A sharp here. So that's this fundamental frequency, plus all of its harmonics. The waveform of a bowed string is very rich in harmonics, so you play that note just steadily, you're generating all of these black vertical lines here. Now you do vibrato, and you move the frequencies up and down, and of course that's all of the harmonics move up and down. Now you follow one of them and see what it's doing. Choose any one and look at the blue curve underneath it. As we go through that vibrato cycle, some of the harmonics are on bits that are steeply sloping upwards. Some are on bits that are steeply sloping downwards. Some are on bits that are near peaks. The curve is moving everywhere. So that when she played that vibrato note, she varied all those frequencies, but by processing it through this wooden box, it's not the same one, but it would be generically like this, something very complicated happens, because each one of those harmonics is not only varying in frequency, but is fluctuating in amplitude, and they're all doing it in different phases and in different ways, and the whole result is something rather complex. And we seem to quite like complex things. Sounds that are too simple we don't like. Sounds that are too complicated we can't latch onto. But there's a level of complexity which can please us, maybe. There are difficult issues lying behind this, but without this jaggedy response curve, you wouldn't get that rather interesting sort of lighting up of the... People usually talk in terms of richness or words like that, of this effective violin vibrato as opposed to electronic keyboard vibrato. So that's one reason why it would not sound at all the same with a flat frequency response, and so maybe it's lucky that they were forced to do things with a mechanical amplifier. Now, let's look at another thing. I said there was a good reason for having holes in our box. Why is that? Well, the basic reason for that is simple. We're reinventing this violin. We have decided the frequency range we wanted to play in, and that we want it to be fairly small. The more portable the better. We're going to play dance music on it and walk around with it. What governs whether the sound is reasonable? Well, the amplification is all to do with these resonances of the box that I was just talking about. So we better make sure that we don't run out of resonances before we get to the lowest frequency we want to play. If there are no resonances at all in, shall we say, the bottom octave of the violin, then those first few notes on the lowest string are going to sound a bit thin and weedy. And this is a familiar sound. It's the sound of undersized violins that children learn on, which all sound thin and weedy. Because when you make things smaller, all the frequencies go up. Smaller things, other things being equal, have higher frequencies. It is hard to make a small, conveniently portable but robust thing which has really low resonant frequencies. We have one trick that we can pull out. Because there are good reasons for making our light structure in a closed box because of the structural efficiency of supporting the load nicely, it just turns out that if you've got a closed container and then you make a small hole in it, you can make a resonance which is a different kind of resonance than the ones we just saw animated for the wood vibrating. Something known as a Helmholtz resonance. And it's the sort of thing that you're familiar with every time you do that. Now that's not the glass bottle vibrating, that's the air inside the bottle resonating when you do that sort of thing. So here's a sort of schematic bottle. And so inside the bottle we've got really solid walls and we've got air trapped inside there. In the neck, you can't see it, but there's a sort of blob of air around the neck which you could think of as a kind of loose-fitting little piston cork in the neck. If we push this yellow bit down, it has to compress all this air that's underneath it. What happens to air when you compress it in a closed space? Well, that's what happens when you put your thumb over the end of your bicycle pump and then push. It pushes back at you. Gas in a confined volume acts like a spring. You compress it, it pushes back. This yellow blob here, what's that doing? That's bouncing up and down on here. It's got a certain amount of mass. So we've got something like a bit of a mass sitting on a kind of a spring, and whenever you sit a mass on a kind of a spring, you get a resonant frequency. And that's the essence of this thing called a Helmholtz resonance. It's all to do with the air, the volume of the box, the size of the holes, and this effective mass and effective spring. And it just turns out when you put the numbers in that it is easier to get a low frequency from a small-sized object by doing this kind of thing than it is by making the wood vibrate in the way that we saw before. There are loads of examples. If violin bodies are absolutely not the only thing that do this. It's that funny noise you get when you open your car windows just a little bit when you're going along and it goes boom, 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 boom. That's the Helmholtz resonance in the passenger compartment of your car breathing through that little hole in the partly opened window. So this has been harnessed in all stringed instruments, guitars, you know, everything. Oh, well, maybe not pianos. There's not a constraint on size of keyboard instruments in the same way. But plenty of other instruments, not only the violin, have a closed box with one or two small holes in it, which introduce an extra resonance, and that we can demonstrate. So she's now going to play a note. You'll see it's quite low down. It's down in first position on the G string. She's just going to play a note that's sitting right on top of this air resonance, and I'm going to come along with this important saxophone mouthpiece bag here and cover one of the holes up. I'm not going to stop the top vibrating. I'm just going to shift this air resonance, and you'll hear something change. It doesn't go silent, but the sound changes. That's because we haven't lost all the high harmonics, but we've removed a lot of the reinforcement. This is the moment to do slackening. If you didn't have that resonance, you get that characteristic sound of bad violins, thin and weedy on the bottom. So that's one trick. Now, I'm going to do one more demonstration and you'll see why this one has to come last. I said I'd come back to the sound post and say something. I've already said it plays a role in strength, but it plays a role in sound as well. Now, schematically, if our violin was as symmetrical as it looks from the outside, and here's our violin cut through the middle, we're applying forces on the top of the bridge, like it says there. What kind of thing do you expect that to do? Well, schematically, it might make things move like that red line there. It's going to make the bridge rock, perhaps. And this is going to push on one foot and pull on the other. And you'd expect the top to vibrate in that sort of symmetrical way like that. Well, vibrating in a symmetrical way like that is a really bad way of making sound. Because while this bit on the left, yes, is pushing and compressing the air, at exactly the same moment an exactly equal area next to it is pushing and sucking the air. Then they swap over, so we've got these equal and opposite things. So we don't have to compress the air, it can just slosh from side to side over the top of the violin and sort of short circuit the thing you're trying to do. So this is not a good way to make sound. Now we put a sound post in our violin. Roughly speaking, we wedge something underneath 1 foot of the bridge, and as a first guess at what that does, it might just stop this point moving, and it just makes it pivot around here. So now we apply our force, and maybe our top does something more like this. It's, not so different from the red line up there, but it's no longer symmetrical. So we're now pushing on this big bit, and only sucking on this small bit. And so they don't cancel each other out. There's some net volume change. Now, if the whole volume of the box is getting bigger and smaller, you have to create sound waves. There's nowhere else for the air to go. It has to get compressed. So symmetrical is bad, lack of symmetry is good. And the sound post has this effect for you. And it's not so unfamiliar. It's these things. It's the reason you put loudspeakers, it's the reason you put loudspeakers in boxes. A loudspeaker is a piece of cardboard or something which you shake backwards and forwards with some kind of electromagnetic doodad. If you have a loudspeaker not in a box, there's no volume changing. The front bit of the speaker cone is pushing, but the back part is sucking, and the air just flows around the side and short circuits, and so you don't make a lot of low frequency sound. You put it in a box, the box doesn't have to do anything except be there. Now we vibrate this, and we've got a piston moving in and out of this box. The volume of the whole thing is fluctuating. It has to make sound waves because there's nowhere for the air to go. It's a really familiar effect to hi-fi people. It's the reason it's so important to connect your speakers in the right phase on your stereo system, otherwise in low frequencies one will cancel the other one out. It's the reason I say that you put things in boxes. So we're going to demonstrate that only once. Because I could knock the sound post down while you're watching, but I can't put one back in while you're watching. In fact, I'm not my violin today, so I'm not even going to try to put it back in. So let me just, in the interest of getting a good effect here, tell you what you're going to hear to make sure you hear it. You're going to hear the same kind of effect that you just heard with the air resonance and covering the whole, except you're only going to hear it once. This is a low frequency effect. This has an effect on whether the lowest components of the note radiate a lot of sound. There will still be sound from the higher harmonics, so it won't go silent, but the sound quality will change in a rather similar way. This is my prediction. So the way it changed with the, when I covered up the air resonance. So she's just going to play in first position on the G string, then I will approach her with this veterinary looking object here, which is a sound post setter, and attempt to do no damage while knocking the sound post out. And this is another of those things, do not attempt this at home unless there is an adult present who knows how to put it back afterwards. Hear that? You only get it once. That's almost the end, but I want to leave you with one more picture, because I don't want you to go away from this lecture saying, oh, this great lecture about the violin, he told us how the violin works. You can say, oh, this great lecture about the violin, but I have not told you how the violin worked. I've told you something like this. When you make a jigsaw puzzle, what do? You build the edge bits first. Not because they show you the picture, but because they're easier. And they kind of put a frame around things. And then you start trying to piece bits in islands that you're not quite sure where they go. And you gradually piece pieces in. Each individual bit doesn't show you much more of the picture, but it's cumulative, and eventually things emerge. That's how science works. You have to start with the easy things, which are not necessarily the most important. Then you put bits in. Each individual bit may not seem all that much, but you have to keep putting them in, and gradually a picture builds up. Here's where violin acoustics is today. We know more than we did. We've got a framework, we've got some islands, bits that we're not quite sure where we go. Send more money and we'll fill some more pieces in. Thank you very much.